Hello everyone, and welcome back to this series on intermediate probability theory, and today we're going to work through an example of how to use the change of variables relation for probability density functions in order to build what is known as the chi-squared distribution. If you ever worked with the chi-squared distribution in statistics or analysis or quantum mechanics, definitely this should be roughly familiar, but we'll see where the PDF comes from and also mention a couple important properties that you definitely should know also. So where does the chi-squared distribution begin? Well, we first off start off with a standard normal random variable, a normal variable that has a mean of 0 and a standard deviation of 1, and we consider the random variable y, which is going to be defined as the square of x. So if you take a standard normal random variable and you square it, a natural question that you may ask is, what is the PDF, or the probability density function, of y? The answer is a chi-squared distribution. Right, so a couple things to start, right? So we have a standard normal random variable, so that's centered around 0, and then we're going to be squaring this random variable, right? So we're going to have x squared. So obviously this is going to range from 0 to infinity and have some shape like this. Because if x belongs to minus infinity to infinity, as a normal random variable typically does, then x squared is going to belong to the left side bounded interval 0 to infinity, which will be the domain of a chi-squared distribution. So if y is equal to x squared, and we try and solve this equation for x, then what we're going to get is x is going to be equal to plus or minus the square root of y. And this is going to be defined to be equal to the inverse relation of x. All right? So once we have the inverse relation with respect to x, then we need to differentiate this in order to use the change of variables relation. So if we differentiate this relation, g inverse of y with respect to y, using our power rule or chain rule or whichever differentiation methods you have, you should get plus or minus 1 all over 2 square root of y. So what we're going to do is we're going to split this up into two domains, one for the right and one for the left. We'll have 1 over 2 square root of y, provided that x is bigger than or equal to 0. So x bigger than or equal to 0 is going to be mapped to this in terms of inverses. And then we're going to have negative 1 over 2 square root of y, provided that x is negative. So when x is a negative number, we're going to be mapping it to the negative variation of that. Right? So once we have that, now we can start to build our probability density function for y with the change of variables relation. And keep in mind, this is going to be the probability density function for x evaluated at x, which is now in the form g inverse of y. And then we're going to be multiplying by the absolute value of the derivative with respect to y of g inverse of y, which some people refer to as the Jacobian. Right? So we're going to be splitting this up into two pieces. So we're going to have x greater than or equal to 0 of g inverse of y times the absolute value of that Jacobian. Let's call it Jacobian right. And then we're going to have fx less than 0 for g inverse of y times the absolute value of the Jacobian for the left-hand side, which I'll denote as JL. Now, the absolute value of this particular object, keep in mind, is going to be the same exact thing. So we're going to have a symmetric Jacobian. And also, when we plug this into the probability density function for x, when you take a plus or minus and you square it, you still get the same exact number. So what we're going to have is, so the probability density function of x is going to be a standard normal. So it's going to be 1 over the square root of 2 pi times e to the minus 1/2 x squared, but x is going to be the square root of plus or minus y. And then we're going to be multiplying that by the absolute value of plus or minus 1 all over 2 square roots of y's. And since they're pretty much the same exact value, both in the exponent and the absolute value, I'm going to be throwing in a 2 here to account for left plus right being equal to the same exact thing, so 2 times one of them, in particular the positive output. So what is this going to give us? So this is going to be 2 all over the square root of 2 pi times e to the minus 1/2 of y, since plus or minus 1 squared is 1, and the square root of y squared is just going to be y. And then over here we're going to have 1 over 2 square root of y, since that's just a positive number. Then we have some cancellations going on here. For example, the 2 and the 2 is going to cancel. And then we're going to have this square root of y term on the bottom, which is going to be mapping to y to the power negative 1/2. And that's going to give you your setup for the chi-squared distribution. Right, so let's just write it formally here. So therefore, Fy of y will be equal to 1 over the square root of 2 pi times e to the minus 1/2 y times y to the power of minus 1/2. Right? And some people may write that bottom 2 as 2 to the power of 1/2 and pi to the power of 1/2. But nonetheless, this is referred to as the chi-square 1 distribution. Right, so the chi-square 1 probability density function. Why is it chi-square 1? Because we only took one standard normal random variable and squared it. Right? So that is our probability density function, which, keep in mind, is supported on 0 to infinity. I'm going to go ahead and write this in a new form because this is going to be a little bit more easier to generalize to the chi-square n distribution. So you can write this equivalently as Fy of y is equal to 1 over 2 to the power of 1/2. And then you might remember that the square root of pi is the same as gamma of 1/2. And then we can write this instead as e to the 1/2 negative 1/2 y, and then multiply by y to the power of 1/2 minus 1. Right? And again, this is the chi-squared 1 distribution. And you may hear some terminology about this number. This is sometimes referred to as the degrees of freedom. Some people will also refer to this as the scale parameter. Scale parameter of the chi-squared distribution. Right? And keep in mind, y belongs to the interval 0 to infinity. Right? So that gives us our first chi-squared distribution. Now let's see if we can build some other things. For example, once you have a probability density function, you might be tempted to find, for example, the expected value, the second moment, the variance, the kurtosis, the skewness, so many things, right? So let's begin by supposing that x is a chi-squared 1 density function, implying that the probability density function for x will be equal to 1 over 2 to the power of 1/2 times gamma of 1/2 times e to the minus 1/2 x times x to the power of 1 minus 1/2, also known as negative 1/2 or 1/2 minus 1. Right? Let's just write it as negative 1/2 just to keep things simple. All right, so once we have that, what will we have? So if we want to find the first moment and second moment, we can either do direct integration, or we can just target the moment generating function for x, differentiate it n times, and then plug in 0 in order to get the nth moment of x. So what we can do here is apply Laplace transforms in order to build the moment generating function of this random variable. So recall that the Laplace transform of a function f is equal to the integral from 0 to infinity of f of x e to the minus x of t dx, and this is going to be equal to, by definition, the expectation of e to the minus xt, provided that the random variable f is supported on 0 to infinity. So just from this definition, we can clearly see that the moment generating function for x evaluated at minus t is just equal to the Laplace transform of the probability density function. Right, so we get this very important identity that connects moment generating functions and Laplace transforms of PDFs. Right? And keep in mind, this only holds if the support of this probability density function is 0 to infinity. That's extremely important. So if you have a normal random variable, this method cannot at least directly work as it does, for example, chi-square, gamma, or even log normal. So let's use this identity in order to build the moment generating function for chi-square 1. So that means mx evaluated at minus t will be equal to the Laplace transform of that probability density function. So this is going to be 1 over 2 to the power of 1/2, gamma 1/2. That's just a constant. And Laplace transforms are linear operators, so constants can factor out. And then we're going to have the Laplace transform of e to the minus 1/2 x times x to the power of minus 1/2. Right? Now, you should remember that this is just going to be a shifted Laplace transform of x to the power of minus 1/2 if you remember your identities for Laplace transforms. So if you don't remember, I'll remind you. So this is going to be 2 to the power of 1/2, gamma 1/2 multiplied by, so the constant for this is going to be equal to -1/2 plus 1, which is going to be 1/2, all over t to the power of that same exact number. And then we're going to add the number that's hanging out in front of this x, and that's going to be equal to 1/2. And always that's the opposite of that sign, right? So make sure, if you don't remember this identity, to try and prove this on your own. And then we can simplify this a little bit, because if we see something very nice, gamma 1/2 is going to eliminate inside of this expression. And notice that 2 to the 1/2 and t plus 1/2 has the same exact power of 1/2. So we can combine them and write this as 1 over bracket 2 times t plus 1/2 all to the power of 1/2. And then we can distribute that 2 in, making it 2t plus 1. And that's going to give us a nice representation for mx of negative t. So mx of negative t will be equal to 1 over 1 plus 2t to the power of 1/2, which we can, of course, write as 1 over the square root of 1 plus 2t. But that's not the MGF of x, that's the MGF of x evaluated at minus t. So we can just switch our domains around, and then we're going to have mx of t will be equal to 1 over the square root of 1 minus 2t. And that, my friends, is the MGF of a chi-square 1. Right, so MGF of a chi-square 1 random variable. It's actually pretty nice. So if we want to build the moment generating function for, say, a chi-square n, even though we don't know the probability density function of it, we can easily build it via properties of MGFs and then go backwards. So let's go ahead and say, suppose that xk are independent and identically distributed chi-square 1 random variables. And let's define y to be equal to the sum from k is equal to 1 to n of these xk's. And keep in mind, this is equivalent to the sum from k is equal to 1 to n of standard normal random variables squared. So a chi-square random variable is just going to be a sum of independent and identically distributed standard normal random variables. So once we define y to be equal to this, then we can easily get the moment generating function using properties of MGFs. So the moment generating function of the sum of these objects is just going to be equal to the product from k is equal to 1 to n of those moment generating functions, the individual ones. So 1 over the square root of 1 minus 2t, and keep in mind each of them, since they're IID, will have the same 1. So we can write this in simplified form as 1 over 1 minus 2t to the power of n over 2. Right? So this is going to be your moment generating function for your chi-square n distribution, and from it then you can inverse Laplace transform and show that the probability density function for y will just be equal to 1 over 2 to the power of n over 2 times gamma of n over 2 times e to the minus 1/2 y. That stays the same, and then we're going to have y to the power of n over 2 minus 1. Right? So that gives us our probability density function, which we refer to as a chi-square n random variable. So that's going to be our superstar identity PDF. All right. And from here you can obviously derive the expected value of a chi-square n random variable. So let's suppose that x is a chi-square n random variable. Then I at least leave to you to try on your own, so you at least have two different ways to show that the expected value of a chi-square n random variable will just be equal to that number n. So you can either integrate the PDF times x from 0 to infinity, or you can take the moment generating function, differentiate it once, plug in 0 in order to get n. It's a very simple number, so please try this on your own, especially if that is one of the expectations. And another thing that you need to find is possibly going to be the variance of this random variable. But once you find the variance, and again, there's a couple ways that you could go about this, but one of the more classical ways is finding the second moment and doing second moment minus mean squared in order to get it. But you might expect that this is going to be very, very complicated looking, but actually it's just 2 times the degrees of freedom. And again, a couple ways that you could go about that. You could find the expected value of x minus mu squared, or you can use the classical approach, the second moment of chi square n minus the expected value of that random variable to the power of 2. That's how a lot of people at least go about it. So that's the chi-square distribution, the mean and the variance formulas. Very, very elegant. And again, if you don't know the importance of the chi-square distribution, there are so many inferential methods, especially associated to the variance of random variables, and also it comes up in linear regression and several other things as well. So what do we have? So we have the chi-square distribution. Chi-square, some people also call it the chi-square distribution also, since it's chi, the Greek letter squared. So the chi-square distribution, which is denoted by chi-square n. So let's just quickly summarize what we've built so far. So we have the probability density function, 1 over 2 to the n over 2 times gamma n over 2 times e to the minus 1/2 to the power of x, and then x to the n over 2 minus 1. And again, this is supported on x greater than or equal to 0. The graph has this skewed right distribution. For n is greater than or equal to 2, and typically n is taken to be an integer, but there's a special case in terms of the graph when n is equal to 1 that has that geometric shape to it. We've also derived the moment generating function for a chi-square distribution, which again is 1 over 1 minus 2t to the power of n over 2. All right, so that gives us our PDF and our MGF. Another distribution that you can easily derive that has a lot of properties is what is referred to as the chi, just chi distribution. So not chi squared, but just chi distribution, where chi n is by definition equal to, take a guess, the square root of a chi squared random variable. And it's going to have the same exact shape, it's just going to have a different skewness associated to it. So how are we going to derive the probability density function for a chi distribution? Well, let's assume that y is equal to the square root of x, where x is a chi squared random variable. So I leave it to you to try and use the change of variables relations. This one's a little bit more easy because our domains are still the same, 0 to infinity, mapping to 0 to infinity. And you should find the probability density function for y will be equal to 1 over 2 to the n over 2 minus 1. That's one difference in the PDFs. Gamma n over 2, that term stays the same. And then e to the power of minus 1/2, instead of y, it's y squared due to the squared property. And then it's going to be y to the power of n minus 1, not n over 2 minus 1. And again, y will belong to the interval 0 to infinity. There are several other properties where the chi distribution comes in. If you ever heard the t distribution, the chi distribution is used in the derivation of that, and we'll get into that in the near future. But one property that you definitely should know associated to chi-squared distributions is the following, and this has a numerous number of applications. So if x is a chi-square m distribution, and y is associated to a chi-square n distribution, and let's assume that these are independent random variables, then x plus y, the sum of two independent chi-square random variables, will also be a chi-square random variable with m plus n degrees of freedom. And this kind of follows as an analog to the properties of linear combination of normals, because when you have a normal plus another normal, you also get a normal random variable, and chi-square has the same exact beautiful properties. And again, keep in mind, chi-square is just a fancy way of saying a sum of independent, identically distributed standard normal random variables. Right? But again, if you don't know the applications, I have several other videos that go into them, but this is some of the backbone theory associated to the chi-square distribution. And we'll get into the other special statistical distributions in the near future. Hope you enjoyed this video, and I'll see you in the next one. Take care.